The Alps. Snow peaks, ordinary postcard Switzerland. But 2,000 feet inside these mountains sits one of the most extreme underground power stations ever built, completely invisible from the surface. Why would they hide something this powerful inside solid rock? This is the Limern Pumped Storage Power Plant, 1,000 megawatts, Switzerland's largest underground power station. To understand why, first you need to grasp the corner Switzerland had backed itself into by the early 2000s. For decades, the Swiss had relied on two main sources of electricity: hydropower and nuclear. Hydropower accounted for more than half of total generation, and nuclear made up most of the rest. The system worked, but it had a fundamental flaw. In summer, the rivers ran fast, the sun was strong, and Switzerland produced more electricity than it needed. In winter, demand spiked and generation dipped. The country had to import power across its borders to cover the gap. Then came the earthquake and tsunami that struck Japan on March 11, 2011, and the disaster that followed at the Fukushima Daiichi nuclear plant. The Swiss federal government responded quickly. By May 25, 2011, the Federal Council had officially committed to a gradual nuclear phase-out. Existing plants would run until the end of their service lives, but no new reactors would be built to replace them. The last plants were expected to close over the following decades. The Mühleberg nuclear plant shut down on December 20, 2019. Others are still running, but aging. The writing was on the wall. Switzerland needed to find a different way to cover its winter peak demand and maintain its position as a reliable electricity trading partner for the rest of Europe. Building more dams was out. The most suitable valleys had already been developed. Wind energy barely makes a dent at alpine latitudes. Solar is seasonal, which is precisely the problem Switzerland was already trying to solve. So the engineers asked a different question. Instead of generating more electricity, what if you could store the surplus electricity that already existed and then release it precisely when and where Europe needed it most? Their answer wasn't to build more dams. It was to go deeper, up into the high Alps, and hollow out the mountain itself. The project had actually been in planning for years before Fukushima accelerated the need for it. Construction on the Linthal 2015 project formally began in late September 2009. It would take almost a decade from groundbreaking to full commissioning. Planning an underground power station of this size means designing around rock instead of around steel frames and concrete pours. Every gallery, every shaft, every tunnel has to be mapped against geological surveys, stress models, and water table data before a single blast goes off. The challenge was not just scale. The machine cavern was to be built about 2,000 feet inside the mountain, at an elevation where normal construction logistics simply do not work. Workers excavated a tunnel approximately 2.5 miles long from the valley floor at Tierfeld. Inside that tunnel runs a funicular railway, the Stanseibahn Linth-Limern, which holds the record as the highest capacity funicular on Earth. It can carry up to 215 tons per trip, or 30 people at a time, which is the kind of capability you need when you're trying to move 220-ton transformers through a mountain. The machine cavern itself, once excavated, measured about 490 feet long, 100 feet wide, and 174 feet tall. The adjacent transformer cavern sits right beside it. Both are carved deep under solid rock overhead. What you're looking at once you strip away the rock is an entire industrial complex buried inside a single mountain. Two head race tunnels, each about 1,000 feet long and angled at 43 degrees, drop from the Mutsee down through the limestone to the turbines below. Near the top, a 130-meter surge shaft, essentially a vertical pressure relief valve, sits carved into the rock to absorb the sudden changes in water momentum when the turbines switch between pumping and generating. At the bottom of those shafts, the water feeds into 4 separate turbine units, each one producing 250 megawatts. From the turbines, 2 tail race tunnels, each 500 feet long, carry the water back out into the Limern Sea below. Beside the mountain cavern, the transformer cavern steps the voltage from 18 kilovolts up to 400 kilovolts before the power feeds into the Swiss grid. High voltage cables then run back out through the access tunnel to the substation at Tierfeld in the valley. From the outside, a visitor sees a dam wall and a few tunnel portals in the rock face. The rest, every turbine, every transformer, every cable, is invisible, buried under 400 to 500 meters of solid limestone. To keep all that rock in place, crews used an extensive system of rock bolts, shotcrete and anchors. The geology presented constant complications. Water inflows through fractures had to be sealed as the excavation progressed. Managing groundwater pressure deep inside a mountain while simultaneously drilling and blasting new galleries requires a level of coordination that pushes well beyond ordinary tunneling work. Hundreds of workers cycled through the project over the course of construction, with major activity running round the clock from the Tierfeld base. Because the mountain's internal transport cable had a weight limit of 40 tons, and the 4 main transformers weighed 220 tons each, a separate underground cableway nearly 2.5 miles long had to be built specifically to carry the transformers to their final position inside the cavern. The funicular simply could not handle that load. The rotors for the 4 generators weighed 330 tons apiece and could not be transported at all. They were assembled on site inside the cavern by the manufacturer Alstom. The total cost of the project came in at 2.1 billion Swiss francs. The engineering principle behind pumped storage is old, but the scale of what Switzerland built here is genuinely striking. Think of it as a rechargeable battery the size of a mountain. The water is the charge. Gravity is the discharge. The turbines are the switch. When the grid has more power than it can use, you run the switch one way. When it needs power back, you run it the other. 2 reservoirs sit at different elevations. The upper reservoir is the Mutzsee, which holds the record as the highest reservoir in all of Europe at 8,117 feet above sea level. Its dam is the longest in Switzerland at 3,458 feet. The lower reservoir is the Lermöntsee, roughly 2,067 feet below the Mutzsee. Between them, 2 pressure shafts carry water down through the mountain to the turbines. When electricity prices are low and the European grid has surplus power, typically overnight or during periods of high wind and solar output from Germany and southern Europe, the plant runs in reverse. The turbines become pumps. Cheap electricity flowing in from the grid drives the machines to push water back up from the Lermöntsee to the Mutzsee. When prices spike and demand peaks, the plant reverses again. Water drops that full 2,067-foot distance through the pressure shafts, spins the turbines, and 1,000 megawatts flows onto the high-voltage grid within minutes. From a full stop to peak generation takes just 120 seconds. For context, that's faster than many conventional thermal plants can respond. This ability to respond that quickly is what makes pumped storage so valuable. Weather is irrelevant. It needs no wind, no sun. It can be sitting dormant at 3 in the afternoon and running at full power by 3:02. The Lermön plant can store up to 34 gigawatt hours of energy, with an overall cycle efficiency of more than 80%. The plant brought the total output of the Linth-Lermön complex from around 520 megawatts up to 1,520 megawatts, placing it in roughly the same league as a large nuclear unit. One plant in a Swiss mountain is impressive on its own. What it represents for the continent is something larger. Europe's electricity grid is in a period of fundamental transformation. Germany has been aggressively expanding wind and solar generation. France and southern Europe contribute large amounts of solar power during sunny periods. The challenge is that renewable generation does not follow demand, it follows weather. On a very windy day in the North Sea, Germany can have surplus electricity it cannot use. On a cold, still winter evening across Central Europe, the grid needs fast response generation and cannot wait for a breeze. Switzerland sits geographically in the middle of all this, connected by high-voltage interconnectors to Germany, France, Italy and Austria. Limern and plants like it can absorb that German surplus, store it as water in a mountain reservoir, and then send it back out as peak power when the grid needs it most. A 10.5-mile, 380-kilowatt overhead line was constructed to connect the Limern plant directly to the Swiss high-voltage grid at Tierfeld. That single line is the thread between a mountain reservoir and the wider Central European grid that can draw on Swiss peak power when demand spikes. The Nantes-de-Drance plant in the canton of Valais, a 900-megawatt pumped storage facility that began operations on July 1, 2022, after 14 years of construction, works on the same principle. Together, these plants represent a growing strategy across the Alpine Arc. Use the mountains themselves as a storage medium, tuck the power stations inside the rock where surface disruption is limited, and let the altitude do the work. Europe is effectively filling parts of its mountain landscape with energy hardware, and Switzerland sits at the center of that network. In 2023, Switzerland exported about 6.4 terawatt-hours more electricity than it imported, even while still relying on imports during tighter winter periods. Switzerland's alpine pumped storage plants are, by almost any measure, a genuine success story. Clean, flexible, powerful, and operating entirely out of view. But they raise questions about what comes next. The hydrology of alpine watersheds depends heavily on snowpack and glacial melt. Switzerland's glaciers are retreating. Research published through multiple European climate bodies has consistently flagged that reduced snow accumulation and altered seasonal melt patterns could affect inflow volumes and storage behavior for alpine reservoirs over the coming decades. A plant that depends on water needs water, and the Alps are changing quickly. In 2023, Swiss glacier monitoring showed that about 10% of Swiss glacier volume had been lost over just 2 years. There is also a question of who these reservoirs ultimately serve. Local communities in Switzerland have genuine interests in how these water systems are managed, including concerns about river flows, local ecosystems, and the trade-offs involved in operating a reservoir as a trading asset for the European electricity market rather than as a regional resource. The question isn't whether Switzerland built something extraordinary here. It clearly did. The question is whether the mountains will keep their end of the deal. Switzerland didn't build more dams. It didn't bet on wind. It looked at what it already had, mountains and water, and built around that. Which country do you think is best positioned to do something similar? Tell us below. Thanks for watching it, and if you enjoyed, subscribe for more Mega Build stories.